So there's metals, molecules and ionic compounds like NaCl, and it's just very confusing all the different types of chemical bondings you can have.
That's a really good question. Bryce Crawford Jr. was famous for saying that the nature of the chemical bond is the problem at the heart of all chemistry. So it is certainly the case that this idea of the different types of material we have and the different types of bonding associated with it is a real issue and is important in our understanding of chemistry. In 1941, Van Arkel came up with a triangle of bonding in which he had the ionic bond with cesium fluoride, the homopolar covalent bond with fluorine or iodine, and the metallic bond with tin. And this is known as the Van Arkel triangle of bonding. A few years later, another Dutchman, Ketelaar, came up with a similar representation, and these two are combined into the Van Arkel-Ketelaar triangle of bonding. In 1993, Bill Jensen published a paper in which he quantified the triangle using electronegativity. It's possible to add many binary materials and elements to Jensen's quantitative triangle of bonding. In 1993, Michael Lang published a paper which talked about a tetrahedron of bonding, because Lang realised that when we talk about covalent materials, there are two distinct types. We have network covalent materials like diamond, and we have molecular materials like iodine or fluorine. Right, so the question is it possible to add Jensen's quantification of the Van Arkel-Ketelaar triangle to the Lang tetrahedron? Is it possible to make a quantified tetrahedron of structure, bonding and material type? Well, the four corners of the tetrahedron, there's no particular problem with the molecular corner, fluorine, as fluorine F2 is a clear molecular material and it's the most electronegative element. There's no particular problem with cesium. Cesium is clearly metallic and is the most electropositive element, and there's no particular problem with the ionic corner, cesium fluoride. But what about the network covalent material? The most electronegative element that forms covalent networks is carbon, and carbon has an electronegativity of 2.55. Therefore, a corner of the tetrahedron should be cut off at electronegativity 2.55. Okay, so here we have the new tetrahedron of structure, bonding and material type. On this side, we can clearly see fluorine F2, the molecular material, in blue, cesium, the metal, in red, and the ionic material at the top of the triangle, this face of the tetrahedron, the triangle, in yellow. And we can rotate the tetrahedron, and we can see how there's a corner cut off. On this side, we can see the corner in red with cesium. At the top, in yellow, we can see cesium fluoride, and then we can quite clearly see the cut-off corner with carbon at 2.55. So this gives us a truncated tetrahedron of structure, bonding, and material type. It's possible to see large-scale images of the four sides of the tetrahedron on the website. It's also possible to download a PDF file, which I advise you to print out at A3 size, cut out the tetrahedron and build your own. The chemogenesis truncated tetrahedron of structure, bonding and material type.